In lesson 7.3, we're still working on evaluating and simplifying exponents and expressions that contain exponents. Specifically in lesson 7.3, we're going to be working on multiplying powers with the same base. When I say base, I mean if we were to have something like 5 to the 7th power. 5 is the base, while 7 is the exponent. Similar to if we had c to the 4th power. C is the base, and 4 is the exponent. So what we're working on today is multiplying those powers, and when they have the same base, we're going to figure out that we add those exponents. So that'll be a rule that you'll want to write down. When multiplying like bases or same bases, we add the exponents. We can expand a couple of them out to show that. We're only going to do a few of them here for these examples. If we look at this first one, we have 5 squared, which would be 5 times 5. And then we have times 5 of an unknown amount. And in the end, we know that we have 5 to the 11th power. Well, we know that 5 to the 11th power would be 5 times 5 times 5, and so on until we have 11 of them. So what we can do is expand it out to make sure that we have 11 in total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 2 of them were from that 5 squared, so the others have to go to the second term. 1, 2, 3, 4, 5, 6, 7, 8, 9. And you'll see here that 5 squared times 5 to the 9th, notice how they are like bases, the 5 and the 5. So what we would do is we would add their exponents of 2 plus 9, which gives us the 11. So we're just going to fill in a few of them. If we look at number 43, a to some power times a to the 4th is equivalent to 1. We have to figure out, well, what a to what power is equivalent to 1? What would make it 1? We learned in lesson 7.1 that anything to the 0 power is equivalent to 1. So somehow we need to make this, instead of it being 1, we need to make it a to the 0 power. So this is what we're working with instead. What plus 4 is equivalent to 0? That would be a negative 4. Negative 4 plus 4 is 0, so negative 4 would be our exponent. If we look at 38, 5 to the 7th times 5 to some other power is equal to 3. 7, since they're like bases, 7 plus what is equal to 3? We could say 7 minus 4 is equal to 3, so a negative 4 would be that exponent. If we look at number 41, like bases, and we're multiplying, so we're going to add the exponents. What plus negative 4 gives us a negative 9, and that would be negative 5. Negative 5 plus a negative 4 is equal to negative 9. So that negative 5 was our missing exponent. If we jump down to number 45, you'll notice that in this one specifically, there are different types of variables. We have x variables and we have y variables. If we start with the y, on the left side of our equal sign, there's only one of them with y. So we know that there's nothing to add together. That has to be a 2. You'll also see that the x variables are on the left side, but they don't show up on the right side. So we have to think to ourselves and figure out what exponent would make that x disappear so we don't have to write it. We have to figure out which one would go there as well. We know that x to the, we'll say to the 0 power, we know that's equal to 1. And 1 wouldn't have to be written as a coefficient. So this also has to be to the 0 power because then we wouldn't have to write it. So in order to make this 0, we have this x to the third, that exponent, plus this exponent. 3 plus what equals 0? This would have to be a -3. So in the end, our expression would be x to the third y squared times x to the -3 is equal to y squared. Let's do some practice where we're multiplying powers, and when they have like bases, we add the exponents. So we want to identify those like bases. If we look at this first one, it's all multiplication. 4 times z times 9 times z again. So it's all multiplication. Because of that, we can use the commutative property of multiplication and change the order. So what I'm going to do is I'm going to say that it's really going to be 4 times 9 times z to the 5th times z to the -12th. And I'm doing that because 4 times 9 is a simple multiplication problem that before we included exponents, we knew how to do. So that's something that we will continue to multiply. We know that 4 times 9 is 36. Plain numbers without exponents, those are going to be like bases to us. And then the next ones we see are z to the 5th and z to the -12th. They have the same base with different exponents. So we're going to add their exponents. Still using multiplication between the 36 and the variables, we'll have z to the -7th power. We're told to simplify it in its simplest form, and negative exponents are not simplest form. So we are not done yet. At this point, we need to move that z to the -7th to the other side, which in the end will give us our final answer of 36 over z to the +7th power as our final answer. If we look at the next one, number 14, again, we're trying to identify all of our like bases. Both variables in this expression are m's, which means they're like bases, and because they're like bases and we're using multiplication, we add their exponents, which gives us m to the 7th power. We could always expand it out to confirm that we're doing this correctly, going back on what an exponent represents. M to the 3rd just means we're multiplying m by itself 3 times, and m to the 4th means there's going to be 4 of them. If we were to write this whole thing, it would be m to the 7th because it's m multiplied with a total of 7 of them. Using this rule just kind of simplifies that so we don't always have to expand it out. For this next one, 5c to the 4th times, there's going to be a 1 here, so we can change the order of that by really saying that we have 5 times 1 times c to the 4th times c to the 6th. Using our commutative property of multiplication, it's all multiplication, so that's why it works. Then from there, we can say that the 5 times 1 is 5, multiplied by, these are like bases, so we're going to add their exponents, giving us c to the 10th power. No negative exponents, no 0 exponents, so this is our final answer. We can do the same thing with number 17. 7 x to the 5th. Again, it's all multiplication. It's multiplication in between the parentheses and multiplication within the parentheses. So we're going to use that commutative property and reorder them. I'm going to put the 7 times 8 next to each other with x to the 5th and x. This is going to be to the 1st, so I'm going to show that one just to remember that it's there. And then simplify what we know. We know 7 times 8 is 56. And if we have x to the 5th and then another x, that's going to be x to the 6th power. No negative exponents, so this is in simplest form. Number 18, if we do it, we have 3x squared times that 1x, 3 times 1 is just 3. Still using that commutative property of addition, just thinking our way through it by multiplying like bases, and then the x squared and the x squared again. We're going to add those exponents, giving us x to the 4th power from that addition. For number 20, all of our variables are the same. So all 3 of them are like bases. One of them has an exponent of -2, then an exponent of 4. This exponent, even though it's not written, is still a 1. So it's helpful to write that. Because they're like bases, we add the exponents. -2 plus 4 gives us just a +2. Then we take that +2 and add the 1, which gives us 3. So we're going to have b to the 3rd power. Notice how I showed my thinking as we went through. Here are just a few extras. We're not going to do all of them, but we might do a couple of the more challenging ones. Let's see, if we look at number 23, we have 2 different variables, 2 different exponents. The parentheses are there, but really what they're showing us is that it's multiplication. X and the y with their exponents, they're being multiplied together. This is also being multiplied together, as well as that second group. Because it's all multiplication, we can change the order of it. So I'm going to put the like bases next to each other. We're going to have x to the 5th. We've taken care of that one, times x to the -6th. Taking care of that one. Also times y squared times y, and I'm going to put that 1 there for the exponent. It's still all multiplication. If we want, we can put those parentheses back in there, but we really wouldn't need them. And then we're going to add the exponents of those like bases. This is going to give us x to the -1st power multiplied by y to the 3rd power. From here, you'll notice that we have a negative exponent. We cannot keep the negative exponent, so this part is going to have to move to the bottom. The y to the 3rd will stay because it has a positive exponent. So in the end, our final answer is going to be y to the 3rd over x to the positive 1st power, which we wouldn't necessarily have to write, but we could in the end. Either of these would be acceptable. This one's just better. Okay, if we look at, we'll do number 24. We'll skip number 21, that's okay. If we look at number 24, again, we have all multiplication between all of them. Inside each group of parentheses, and then in between each group, because they're back-to-back parentheses, that's also multiplication. So with that, we can change the order to make it a little bit easier. I'm going to put all of the lonely numbers next to each other, those coefficients, and then follow that up by all of our variables, x to the 5th, y to the 6th, x squared. Really, we can put these x's together, so once I simplify these two together, 5 times 3 is 15, 15 times 3 is 45. Then I'm going to say that we have x to the 5th times x squared times y to the 6th. I just put those next to each other because they're also like bases, and then from there we can simplify those two terms, giving us x to the 7th, y to the 6th. We don't need those dots in between to show multiplication because it's still multiplication when those variables are right next to each other. We just want to make sure that it's clear to know where each exponent goes all the way through. I'll write the answer for number 6 as well. Just changing the order. We have like bases, so we can say that that's x to the 10th times y squared. It's always nice to keep them in alphabetical order. And then for number 27, the last one on this page, putting those like bases next to each other, a to the 6th times a squared times b to the 3rd times b to the -2nd power. Then we're going to combine those exponents, those like bases, by adding the exponents just like before, giving us a to the 8th power multiplied, again I don't need to show that dot, b, 3 plus a negative 2 is a positive 1, so in the end we wouldn't need to show that positive 1, so a to the 8th times b would be the correct answer, or an acceptable answer. Then we have a problem like this, where it looks like scientific notation, which each of them separately are, and when you see a problem that starts in scientific notation, we want our final answer to also be in actual scientific notation. So that's something we're going to check here. Again, it's all multiplication throughout the whole thing, including those exponents. So what we're going to do is use that commutative property to change the order and make it 3 times 6 instead, also multiplied by 10 squared times 10 to the third. From there we know that 3 times 6 is 18. Then we'll be multiplying by 10 like bases, so we add those exponents, which is 5. Then from there we need to rewrite this 18 so that it actually fits within scientific notation. So what that's going to look like is 1 and 8/10. So we want it to have the same value as the 18, so we would have to multiply it by 10 to bring it back to that 18 value. 1 and 8/10 times 10 is 18, so at that point those two are the same. We must remember that we still have to multiply by 10 to the 5th. So from here we can simplify our like bases again while it's still in scientific notation. So our final answer is going to be 1 and 8/10 times 10. Notice how we're using the x now because it's scientific notation. And then we would add those exponents because they are like bases to give us 6. And this is our final answer for this specific problem because it started out as scientific notation. Sometimes we'll have expressions where we need to simplify them first, and that's what we worked on in lesson 7.1, where we would simplify before we evaluated or before we substituted in either of these values. So that's what we're going to do here. We have a negative exponent, so that we're going to move to the bottom, giving us the expression 3y to the 4th over x to the 3rd. Now at this point, now that the negative exponents are simplified, then we'll plug those numbers in, and I encourage you to simplify first because then we will have less confusion as to what those negatives mean in the exponent with numbers next to it, because I find students make mistakes when they try to plug it in first. So we're going to simplify, then substitute it in. So then from here, we'll rewrite this as 3 times y in parentheses to the 4th power over x, which is now a 3, we'll put that in parentheses as well, to the 3rd power, and simplify. We'll take care of exponents first, so it's still going to be 3 multiplied, 1 to the 4th power is still just 1, over 3 to the 3rd power is 27. Then from there we just have 3, because 3 times 1 is 3, 27th. And then we can simplify that fraction because they are both divisible by 3, giving us 1/9 as our final answer. That's just, again, simplifying and evaluating with those exponents. So here's a few that we can practice with. All right. You'll notice in this top one that this fraction bar line, that's division. And then we have like terms. I'm going to write it again just so it's a little bit bigger. It seems to be pretty small. What I like to look for is in either the numerator or the denominator as a group, if there are any like bases that we can combine together. In this one there is. We do have a like base, and we're multiplying those like bases. So we're going to simplify that as is. 3 plus that negative 7 gives us x to the negative 4th power. At this point, there's a negative exponent, so we have to, 1, give it a coefficient, and then bring that to the top because it's negative, which gives us 1x to the 4th power over 1 in the denominator. Because it's in the denominator, we do not need to keep it, so really in the end, 1x to the 4th, or just simply x to the 4th, would be acceptable answers for this problem. We're going to do the same process for number 59. We have like bases in the denominator, and they're being multiplied. So we're going to add them. I'll write it again just so it's a little bit bigger to see. Those like bases. When we add them together, we get 1 over a. 4 plus a negative 3, or 4 minus 3, gives us just 1. So our answer is going to be 1 over a. This time, the 1 in the numerator is needed because that's how it keeps it as a fraction answer. So this would be our final answer. If we look at 60, I'll write it again so it's more visible. We have 4 over c times c to the negative 5th. Again, we want to combine any like bases by adding their exponents. This c right here has an exponent of 1, and that's why it wasn't written. But the c was still there. From there, we have 4 over. We're going to add those exponents. 1 plus negative 5 gives us c to the negative 4th power. Then from there, we'll give that c a coefficient and bring the c to the negative 4th to the numerator, which gives us 4c to the 4th over 1. And in this case, because it's in the denominator, dividing by 1 doesn't change the answer. So it's just going to be 4c to the 4th power. One thing I want you to notice between the top half and the bottom half, everything in the top half was considered multiplication or division. They're inverse operations, which is why that commutative property always works so well for us. You'll notice in the bottom, we no longer have just multiplication. 61 and 62 have addition in them, and 63 has subtraction with parentheses. And when we have addition or subtraction, we are going to have to distribute and then be really careful of those like terms. Not just like bases, the term altogether, meaning the base and exponent, have to be alike. So let's do number 61. If you look at it, this 2a to the thirds is what's going to be distributed to both terms. And these problems can be a little bit challenging, so they'd be something good to write down. When we distribute it in, it's also really good to just show that we're multiplying them. 2a to the third being multiplied by 3a. That's the first distribution. Then we have our addition sign, and we'll do the same thing again. 2a to the third multiplied by 1. From there, we can simplify our separate terms. The 2 and the 3 are similar, so 2 times 3 is going to give us 6. And then we have a to the third and a to the first power, which gives us a to the fourth. We could do that because it's multiplication. Now we have our addition sign, so that addition sign splits that entire expression in half. We deal with one side, then we deal with the other side completely separately. When we look at the second half, we have 2 and 1. Both of them are coefficients, or just plain numbers, so we can multiply them together like they are, giving us 2. And then the a to the third stays the same because there's no like base to match with it. In order to add these terms together, they would have to have the same base and the same exponent, meaning same variable, same exponent. In this case, they don't have the same exponent, so we cannot add them. And this would be our answer. For the next one, again, it's a similar idea. This 8m to the third, all of that is one entire value after it's multiplied together. So the whole thing is going to be distributed in. So we want to show that distribution. 8m to the third is being multiplied by that first term, m to the fourth. Then we have our addition sign, and we're going to distribute the 8m to the third times that 2. Then from here, we can multiply the separate parts. So we're going to deal with the first half in front of our plus sign and simplify that. We have a 8m to the third. This would be a 1m. So right now we're going to do 8 times 1, which is just 8. And then m to the third, m to the fourth, those are like bases. So those two we can combine by adding their exponents, giving us m to the 7th power. Then we have our separating addition sign. And for the second half, all we can multiply together are the 8 and the 2, because there's just one variable. So we don't have any like bases. So then we'll have 16m to the third. Again, to be able to add them together, they would have to have the same variable with the exact same exponent. We cannot add because they are different exponents. And then this would be the final answer for that one. If we look at number 63, it's a similar process, but now we have signs that we want to be careful of. I'm actually going to change this subtraction in here as adding a negative 10. So it may be helpful to rewrite the whole thing so that that's clear. We're going to add a negative 10x instead, because that'll help with that distributing. So with that first step, the negative 4x to the third is what's being distributed in to both terms. When we do that, we get negative 4x to the third multiplied by 3x to the third plus, and then that second term. Again, it's a negative 4x to the third times the negative 10x this time. We made it adding a negative, so that negative needs to be there. Again, this addition sign is a separator in the middle of our expression to keep the two parts separate. So we're going to take care of the first half by multiplying those numbers together. Negative 4 times 3 gives us negative 12. The x to the third and the x to the third, they're like bases, so we add their exponents. Notice how there's different operations happening constantly, giving us x to the 6th power. Then from there, our addition sign can come straight down, and we can work with the second half of our expression. When we do that, we can multiply the negative 4 times the negative 10, giving us a positive 40. And then looking at our like bases, we have x to the third, and x, since there's no exponent, it means there's a 1 there. So when we multiply them and add those exponents, we get x to the 4th power. Again, they are not like terms because they have different exponents with those like bases. So then this would be our final answer. The reason we went through the difference here and having to distribute is because sometimes we have problems that are set up as geometry problems, and you'll have to do this process. For both of these problems, we are trying to find the area of the figure. In number 47, we have a rectangle. And in order to find the area of a rectangle, we have to do length times width. We're given two measurements. If we say that this one right here is the length, and this one right here is the width, we would have to multiply those two together. However, 3x squared plus x, that's one value. So that has to stay together using parentheses. So when we show this, I'm going to say that we have that 3x squared plus x, that's the length all together, multiplied by the width, and the width in this case is going to be 2x. So we have our length, 3x squared plus x, multiplied by our width of just 2x. Again, it's not just multiplication. We have that addition sign in there, right here. So that means we're going to have to distribute this 2x in to both terms. And we're going to show that distribution. And the order of it could look slightly different. Multiplying it by the first term, we're going to have 2x multiplied by 3x squared. Both of those terms will be multiplied together, whether it's 3x squared times 2x or 2x times 3x squared. Either one would be the same, because at this point, this group is all multiplication. Then we'll add and do the second distributing, 2x multiplied by that 1x, or x. We still have this addition sign, so we're going to simplify each half separately. 2 times the 3 gives us 6. The x and the x squared, we add them because they're like bases, giving us x to the third. Then plus, and we'll do the same thing up here. 2 times 1 is just 2. X to the first power times x to the first power gives us x to the second power. Then from here, they're not like terms. Yes, they're the same variable, however, these exponents are different. We're looking at just these portions to see if we can combine them, and in this case we cannot. So this would be our final numerical answer. Then from there, we're talking about area. Area is in square units, so that's the label that we would put there. Square units, to prove that this is our area. When we look at number 48, it's a similar idea. We're still finding the area of the figure. This time, based on these 4 symbols, our figure is a square. We could still think of it as our length times our width to find that area, even though it's a square. And especially since we haven't learned our power to a power rule, we're going to continue using this. If 2x squared fits here, that means it's also 2x squared on this side, and 2x squared on this side, and 2x squared on this side. But we're still finding the area, which is all of the area inside the figure. So we're going to multiply them together, giving us 2x squared times 2x squared. And this specific one, because there's no addition, we don't have to worry about distributing. We can just multiply them together as is. 2 times the 2, because they're coefficients, giving us 4. And then we have our x squared and x squared, so we're going to add those exponents, giving us x to the 4th power. And again, we're working with area. We don't have a measurement, so it's going to be square units as our final answer.